A2 Maths, friction. Okay, so you've got a block sat on a slope and the block is at rest. And all I'd like you to do, please, is have a go at sketching the force diagram showing all the forces acting on that block. So it's sat on rest on a slope. Okay, so just pause there, have a quick go at drawing that. Okay, so hopefully you thought it's got a slope, so let's do a rough sketch of a slope. I'm going to call it an angle theta, just to help me discuss it with you in a minute. So we've got a block sat on there with an angle theta. Let's put a pen on. We got the block sat on the surface. There we go. And what we know is that there's definitely a force due to its weight pulling straight down. So we could definitely put that force on first of all. This block is being pulled straight down towards the centre of the earth. But there's a reason why it's not just ploughing straight into that block, sorry, into that slope, is because the slope is exerting a force off it perpendicular to the slope itself. So we know there's another force acting perpendicular to the slope, which we're going to call the normal contact force, R. So we've got those two situations. Now, normally, this would be moving. We'd have a situation where because part of the weight, which you can see here, part of the weight is pulling down the slope parallel to the slope, then clearly it should be moving down because there's a force pulling it down. But the situation is that it's not moving, it's at rest. So what's stopping that block sliding down the slope? There's got to be something else acting on it. And from what we see here, there's nothing else that's written about. We've not said that it's been pushed or pulled or anything like that. So there's got to be something stopping it moving. And the answer, of course, is friction. A frictional force stops that block from moving. And I know it's got a frictional force because of that key word up there, a rough slope. Everything or most of the things we've dealt with at the moment have all been smooth slopes. Okay, they've all been smooth slopes. So in the situation where it's a smooth slope, there's no friction. But as soon as it's rough, there is this extra frictional force that's pulling up the slope. Okay, right. As the angle of the slope changes, does the magnitude of any of those three forces change? So is the magnitude of any of those three forces dependent on the slope, is the question. And the only thing I'd say at the moment is just have a think about this. Weight is acting down. If I think about the components of that weight, parallel and perpendicular. So let's look at parallel first. So it's like that distance is pulling down. All right. So that much is pulling down the slope. So the frictional force there, because it's at rest, must be equal to that much pulling down the slope. The normal contact force must be equal to that much of its weight. Most of its weight is transferred towards the slope, so therefore the R value is going to have to be quite big to overcome that weight, to equal that weight, to stop it digging itself into the slope. So those two have got to be equal. Okay, right. As I change, just have a think about whether they remain the same, the R, the F and the weight, or whether they change. Okay, so there's a slightly steeper slope. So on the slightly steeper slope, do you think any of them have changed? Do you think any of them have stayed the same? So let's think about it steeper. Okay, so we look at that situation. Has the magnitude of the R value, the F value, and the weight stayed the same or changed? One more. So this is quite a steep slope now, isn't it? It pretty much looks like it should be falling down that slope. All right, if we go much more, it will just literally just fall straight down. So why is it still not moving? Well, it's still not moving because the frictional force hasn't been overcome yet. And that frictional force, if that hasn't been overcome, look how much or look how big it has to be to overcome all this weight that's pulling down there. If I look at that as a triangle now, how much of that weight is pulling down the slope? Well, a lot more than it was when it was shallow. When it was quite shallow, this was quite a small amount pulling down. Now it's got quite steep, we can see there's quite a lot of the weight pulling down the slope. But also, the normal contact force has gone quite small. So the normal contact force just there is actually a lot smaller, which means that the magnitude of the weight has stayed the same, but friction and normal contact force have changed. And that's because friction and the normal contact force are very closely related. Right? Frictional force is to do with the normal contact force. If the normal contact force is quite small, then it's likely that friction will be strong enough to stop it moving. Whereas if the R value gets quite big, it's going to need quite a lot of friction to overcome it. So they're quite closely related. Right, what does that mean then? Well, that means that weight has got nothing to do with it. The weight has got nothing to do with frictional force. It's to do with the normal contact force. But is that the only thing that affects friction? Is the R value, is the normal contact force the only thing that affects friction? Okay, so we just said that. So the answer is no, of course. If you imagine that that block was made out of a different material, so in this case, we could say that this is maybe made out of some sort of sandpaper and this was a sandy wall or something like that. So therefore it's not moving because they've got quite rough against each other. Okay, and friction would have to be so it's unlikely to move. But if we made that out of a different material, say for example out of ice, it's more likely that it will just slide down the surface. So what the material is for these two things makes a big difference of whether it's going to slide or not. So it's not just the R value, not just the normal contact force that affects friction, but there's got to be something else that's to do with the actual material that they're made out of. So friction is definitely made out of two things. It's to do with the R value, the normal contact force, but it's also to do with the type of material that the two surfaces are connected together with. Okay, right, so let's have a look at this without the slope then. So the slope was a nice demonstration to show that the R value is to do with friction, but let's just have a quick think about putting it on a flat surface. So there's my flat rough surface just there. Here's my box. All right, you can think of that as a box in your house and you're trying to move this box. We know that the weight pulls down and the R value, importantly, the normal contact force is going to be equal to the weight. So when the block is on a flat surface, the R value is identical to the weight. Okay. Now, if I want to move that box, you know that if it's very heavy, the R value is going to be quite big, right, to stop the heavy items from falling through the floor. So the R value is very big, so it's going to be quite difficult to move. And that makes sense logically. The heavier it is, the harder it is to move, the more force you need to move it. If it's a light box, you don't need to exert so much force. So let's have a think about just putting a little bit of force on this. We're going to put it as P, and we're going to try and move in that box. Now, the reason it wouldn't move is not because we're not strong enough, we're just not putting enough force in. But the reason why that box doesn't move is because another force, friction, acts against you. And the frictional force is acting, as it would do, in the opposite direction to what the motion is trying to do. So the box wants to move this direction, so friction always acts in the opposite direction. Okay, it's always opposite to both the force acting on it, but the direction the box wants to travel. Now in this case, because the box isn't moving, the frictional force is quite low. In fact, if there was no force there, friction would be zero. Okay, so this friction is directly proportional to how much force you put into it. What happens if I increase the force? So if I increase the force, there you go, then friction will match it. It will increase to stop you moving the box. Okay, if you increase the force even more, you try pushing really, really hard, what's going to happen? The frictional force will again match it because you haven't overcome that friction. Question is, what will happen if you keep increasing the force? So you keep pushing more and more, you get one of your friends to come and help you push it. What's going to happen? Well, if you increase the force to a certain extent, to too much, then friction will not be able to match it anymore. And therefore you will overcome friction and the box will slide across that surface. Okay, and you can see that in everyday life all the time. When you're trying to slide something like a box along the floor, if you're in that situation, you've got to exert enough pressure, enough force to overcome that friction acting in the opposite direction. Okay, so what I'd like you to do, just grab your notebooks then, please. You can do a quick sketch. It doesn't have to be a work of art, so a quick sketch in your notebook of a block resting on a rough surface. And what we've got there is a couple of extra bits of information. What's called the coefficient of friction. Now, the coefficient of friction is the Greek letter mu, and it's the ratio between the normal contact force and the frictional force. Okay, so the ratio between these two things just here is called the letter mu. Okay, so just grab your notebook, get down what you need, pause there while you take your notes down, and then carry on once you've taken down the first bits. Okay, so another key word, limited equilibrium. So in the situation we can see there where you're pushing and the box is just about to move, you put any more force on there, the box will slide. Okay, so you don't put any pressure on it at all, then clearly the friction is zero. You can put in a little bit and friction matches it, and then friction keeps matching it more and more you push, up to a point where the box is about to slide. Now the point when that box is about to slide along the floor, that's called limited equilibrium. It's been in equilibrium all the time up to that point, but at that point is called limiting equilibrium. And you get key words like the box is about to move. Right, the block is about to slide. If they're talking about those about to do it, then you're talking about it being in limiting equilibrium. Now in limiting equilibrium, then you can calculate the coefficient of friction as the frictional force divided by the normal reaction force. If it's not in limiting equilibrium, then because this is only what this is, okay, so this could be very, very small, like this is practically zero, then you're going to have the mu value of practically zero. Okay, so you can only really calculate mu at the point when it's about to move. Okay, so the mu value can start at zero and it can go all the way up, and the point when it's about to move, that is when you've got your mu value. And the mu value does depend on the type of material it's made out of. So different materials have different mu values. Okay, so again, pause if you need to. Okay, so this is the important box though. At the point of limited equilibrium, we get that friction equals mu r. So if you've got the coefficient of friction, and the coefficient of friction comes between what these two types of materials are. So let's say you're doing something made out of a wax block on a stone surface. Okay, and you could do an experiment, you could find the coefficient of friction between the wax block and the stone surface. That coefficient of friction is just a number, just a value, and it will be the same for any wax block on that stone surface. So you can calculate your mu value, and once you know your mu value, you can always calculate your friction once you know your R value. And of course the R value does depend on the weight, or if it's on a slope, the amount of weight that's pulling against the perpendicular to the slope. So it does depend. But remember, it's not the weight that's important, it is the normal contact force. Okay, so I'll pause there, or you can pause there, get down what you need before we move on. Okay, so forget limited equilibrium. What about just in equilibrium? Because if you just left the block on its own and didn't put any force on it, it's going to be in equilibrium because its weight will be equal to its R value. So it's definitely in equilibrium to start with. It's not accelerating in any direction. But what happens if you put a little bit of pressure on and force matches it? Well, it's still not moving. It still doesn't have an acceleration. So therefore, it's still in equilibrium. And in fact, it stays in equilibrium up to its point of limited equilibrium. Now, before that, the frictional force starts at zero when this equals zero. And as this picks up, this frictional force increases. Now, we know that once you get to the point where it's limited equilibrium, it will move. But before that, when it's just in equilibrium, you can say that friction is anywhere between zero from when it starts up to its limit in equilibrium. Now, we don't really care about this part, okay, because clearly that makes sense that friction would equal zero if there's no forces acting on it. So therefore, we only really concentrate on this part of that inequality, that friction is less than or equal to mu r. And that is an important fact. A body is in equilibrium when friction is less than or equal to mu r. So you need to be careful with the language. If they're talking about it being in equilibrium, then all you can say is that the force has not been enough to overcome friction. So the frictional force could be anything less than or equal to mu r. Okay. Whereas if it's in limiting equilibrium, then it's definitely equal to and it's about to move. After that point, it's going to overcome it and it's going to move. So just add that box just there. That's the important one. And you need to understand what that means. That friction is less than or equal to mu r. It's in equilibrium at that point. Okay, so pause if you need more time. So the coefficient of friction definitely depends on the two materials that are in contact. So I mentioned this a minute ago when I talked about the wax block and the sewn surface. But it's worth just putting down your notes that the coefficient of friction, that mu value, depends on the two materials. And the lower that mu value, so if it's a very low value, like 0.01, let's say, okay, means that you need less force to overcome it. Right? Think about what that previous picture is here. F is between 0 and mu r. So if that mu value is something like 0.01 or something like that, times by whatever r is, you can see that it's quite a small threshold between 0 and 0.01 r. Okay. Clearly if it's a very, very heavy object, then that will be a bigger value. But the mu value, the smaller it is, the more likely it is that you would overcome friction. Something like an ice cube or an ice hockey puck on an ice rink has a very low mu value. That's why the ice hockey puck slides quite comfortably over the ice. Okay, and the opposite is true, of course, as well. The bigger the mu value, the more you have to, the bigger the force has to be to overcome the friction. The mu value is what we call dimensionless. Anytime it mentions the word coefficient, a coefficient does not have any units. Okay, and if you actually look at the equation here, you can see that force is in newtons and r is in newtons. That is why the mu value doesn't have any units, because you've already got newtons equals newtons. So the mu value has no units attached to it. It is just a number. Just a number. Okay, so again, just pause while you get those last little bits of notes, and then we'll have a look at a question. Okay, so let's have a look at an exam question on this then. So we've got a child sat in a toy car with a combined mass of 19 kilograms. The only hint I'd say there is, because the child and the toy car have a combined mass of 19 kilograms, you could just draw those on your force diagram as a basic block. Okay, just a rectangle that just represents the child and the toy car. Another child is trying to push her along the rough surface. Okay, force 35, angle 10 degrees above the horizontal, but the car does not move. Okay, so what I'd like you to do, please, is I'd like you just to obviously get the question down in your notebook, as it's saying there, because it's an important question. But then I'd also like you to have a go at drawing that force diagram yourself, please. Okay, so let's see what you got then. So on your force diagram, so if you haven't drawn one yet, pause, have a go at doing it yourself, please, rather than just copying mine straight away. Okay, so I don't expect you to think of it as an art lesson. We don't need to draw this elaborate toy car. And the toy car, we're making this assumption that it's not on wheels, because that causes all sorts of other problems. So it's just a box with a child sat in it, and they're trying to move them along. So I can draw that. I can draw the child sat in the toy car. There they are. Another child is trying to push this box. Now this is important. A force of 35 newtons at an angle of 10 degrees above the horizontal. So there's the horizontal, and 10 degrees above it is like that. So this child is stood here pushing downwards on this car. They're trying to move it, not by pushing straight down, because that clearly would be stupid, but they're pushing it there, but they're pushing part of their force down towards the ground as well. So they're not actually helping themselves here. It'd be easier to push it parallel. So they're pushing down 10 degrees. Let's draw that on. Now, clearly, as we discussed before, it's not ideal to put the arrows pointing into your force diagram. It makes more sense to put that on the other side just here. So we can change that to that side. It makes more sense to put it on there. Okay, so the child is being pushed 35 degrees above the horizontal here. So that will be below the horizontal on this side. So there we go. Okay, so that's what's happening so far. So part of that force this child's trying to move is actually making life more difficult because they're actually adding to the R value. Okay, so what other things are happening then? Well, of course, you have its weight. All right, its weight is pulling down. It's got a mass of 19 kilograms, an acceleration due to gravity of g. So therefore, it's 19 times g. We've discussed this before. It's F equals mass times acceleration. So that's where the 19g comes from. So we've got that part of its force. What else? Well, of course, it's got its normal contact force. This child is sat in the toy car and the floor is pushing back, equal but opposite to the 19g and a bit of this extra force that's pulling down here. So the R value is definitely acting on it there. And it's not moving. Because clearly at the moment, it should be moving if it was on a smooth surface, because you've got the forces acting in this direction, right? You've got 35 sine 10 pushing in this direction. So what's stopping it moving? A frictional force. Friction is acting in the opposite direction to the other forces, and it's acting in the opposite direction to the direction that the box wants to travel. So the box wants to go in this direction, but friction is stopping it. Okay, so frictional force acts in the opposite direction. Okay, so I think we've got everything from the question onto our force diagram. Now we're in a position to resolve the forces in the two directions. So I'm going to resolve vertically to start with. So we're looking at up and down. And the reason for that is then I can ignore friction completely and calculate just the R value. My goal is to get the coefficient of friction. Okay. The other key word, it does not move. So we're looking at the box just about to move. So you're looking at the trying to find the coefficient of friction. So we've got the R value, which we can work out by just resolving vertically. So what forces are acting on this vertically? Well, definitely the 19g pulling down. Definitely 35 sine 10, just there. Remember, it's separate, so it's sine 10. And that's going to equal the R value. Now we got G as 9.8, so therefore we can take 192.3 newtons as our R value. We can also do exactly the same. It didn't matter which way around you did these, but we can do it horizontally as well. Because horizontally, we can see that all the forces pushing in this direction must be equal to all the forces pushing in that direction, because it's in equilibrium, it's not moving. So we've got 35 connected 10, so cos 10, so 35 cos 10 must be equal to frictional force pulling in that direction. So we've got F equals 35 cos 10, which of course equals, once you get your calculator, 34.47 newtons. So I've got my R value, and I've got my frictional force just there. So how can I work out my coefficient of friction? Well, the coefficient of friction at that point just there, okay, so at that point just there, it doesn't matter, it's not in limited equilibrium. It's just talking about the coefficient of point at that single point. So what's it going to be? It's going to be the ratio between these two. So we know that friction equals R when it's just about to move. So in this case, the mu value is 34.47 divided by 192.3. So the mu value at that given point just there is 0.179. Now in the question, it doesn't state that, it just says the car does not move. So it's just not really indicating that it's limited equilibrium. You can assume it could be given to you in the question, but it's important to notice that this mu value just here, this 0.179, is not necessarily at the point of limited equilibrium. And in fact, it could be that that mu value could be higher if this box still doesn't move with more forces pushed on it. Okay, but at that point just there, we definitely got a mu value of 0.179. Okay. Okay, so what I'd like you to do is just have a quick go at the exercises on those 3 pages. So there's lots to do with force diagrams in there. There's some to do with slopes. There's some to do with overcoming friction. There's limited friction. So there's lots of different questions. So take your time with it. Don't rush through it. Have a go at those 3 exercises on those 3 different pages, please. Okay. So straight away, just grab your notebooks. So we've got a block of weight 147 newtons. All right, so it's giving us a weight straight away. And this is slightly different. It's sliding along a rough horizontal surface. So the box is sliding along. So there you go, sliding along. But what we notice is it's slowing down. Right, so you imagine you kick a box along the floor. It's not just going to keep going forever. It's going to slow down and stop. And that's what's happening here. So the box is there. What I'd like you to do is calculate the coefficient of friction. So I know it says your notebook, but what I'd like you to do is just get down your notebook, pause, and then we'll let you have a go yourself. So have a think about what things you know. Okay, so hopefully you thought, because I've got the weight just there, I know that weight is going to be mass times gravity, so I could actually calculate things like the mass. Why is it important to calculate the mass? Because the other equation, the only equation I really know what to use is F equals mass times acceleration. And because I've got an acceleration or a deceleration in this case, then I could be working out the force needed to slow it down by 3. So if you want to just have a go yourself now with those hints, by all means do so. Right, so my force diagram looks like this. There's my box. It's got 147 newtons pulling down, right? Not 147 G, 147 newtons are pulling downwards because the G's are already in there. Obviously, equal to that is the R, so R is going to be equal to 147 as well. We've got friction that's acting in this direction, but it is moving as well. So we can certainly say that it's moving in this direction. Now, we don't put velocities on our force diagrams, but we can show accelerations on our force diagrams using a double arrow. So it's accelerating or decelerating in this case at 3 meters per second. Notice that because it's traveling in this direction, all right, so it's traveling in this direction, friction is acting against it, the direction of motion, as it always would be. So it's sliding along here, but friction is slowing it down. And it's slowing it down at a rate of 3 meters per second. Okay, so what I'm going to use, F equals ma. Be careful, that F there in this formula is all the forces acting on the block. Now in this case, the only force acting on it is the capital F friction. So we need to calculate the mass though. It's no good trying to just put 147 in there because that's not the mass. But we can calculate the mass because we know that 147 is the mg. So a little bit of rearranging, 147 divided by g will tell us what the mass is. So a mass of about 15 kilograms. So we've got a mass of 15 kilograms, noticing the difference between mass and weight there, which is important. So we've got the mass of 15 kilograms. We've got our acceleration as well. So we can do that, put that down as 3. So therefore, the frictional force is going to equal 45. Remember, it's 45 going in this direction, going in the negative direction. Okay, so be very careful. Yes, its velocity is in that direction, but we didn't put -3 down because we're taking this as our positive direction. That's 3 there, that's F there. If you took that as your positive direction and did that as -3, then this frictional force would have come out as -45, which is fine because it's pushing in the back direction. Okay, so it doesn't really matter as long as you're consistent with your sign. So if you did -3 and -F, that's perfectly reasonable. Okay, so I've got that so far. I've got F equals ma. I found my total force as 45, but now I can work out my frictional force. All right, they're different. That's the total force just there. This is just a frictional force. This is just that one force. Okay, so frictional force equals mu r. It's working horizontally to get the coefficient of friction. So I've got 45 as my frictional force. My r value is 147 because it's equal to the weight. So therefore my mu is going to be 0.306. So you can calculate the mu value using things like acceleration. Right, 3 more exercises to have a go at. So these start to link a bit more to do with the Suvat equations to link acceleration. So again, plenty of work for you to be getting on with. All right, plenty of practice. So don't just skimp with them all. Do make sure you're having a go at plenty of those. You've got plenty of time, so do plenty of the exercises. Okay, so we're going to look at a last example, more complicated example, but it also just allows us to look at some of the stuff you did last year to do with what we call connecting bodies. So we've got a block hands, as you can see there, on a light inelastic, so it's not bouncing up and down or anything silly like that. It's light, so the weight of the string or the weight of the rope doesn't come into it at all. So we've got this mass of 100 kilograms over a smooth pulley on a block B. So you can see that depending on the weight of block B and depending on the surface connecting to will dictate whether B starts to move up towards the pulley, or maybe B is quite heavy and it will start moving A upwards. Okay, we all know another bit of information. We know that the coefficient of friction between the block and the surface is 0.15. What we want to do is consider what could happen to block B. Now, realistically, I've just spoilt this for you. I've just said that block B could move down the slope, all right, and pull A up, or it could move up the slope towards the pulley, or it could do something else as well. Yeah, the answer is, of course, it could be in equilibrium, therefore it doesn't move at all. There's no movement to it in the slightest. It would just stay stationary. So those are the sorts of situations that we could be looking at in this situation. Okay. What I want to do is I want to, given that the model is in equilibrium, okay, it is in equilibrium at the moment, so it's not moving. Right, it's exactly the same as what you see there. What are the possible values for the mass of B? Now, it seems quite strange because you expect it to use one value, but it's not. Okay, there's a whole range of values between where it's overcoming friction and not to when it won't move. Okay, so what I want to do is figure out what those values are. So maybe you have a think about how you can go about doing that while you take down what you need for your notebooks. Okay, so there's two situations. There's a situation where the block is about to move up the slope. In other words, A is too heavy and it's about to pull B up the slope. So in that situation, we want to consider B moving up the slope. It's about to move this direction. In which case, what's stopping it moving? Well, friction could be pulling downwards. So the B wants to move up the slope because A is pulling it, but friction is pulling down here. That would give us a certain value for the mass that way. But the other situation could be that B is about to slide down. B is a lot heavier. It's about to slide down the slope and A is about to go up. Well, in that case, because it's about to travel down the slope, then the frictional force would act in the opposite direction and therefore will give you another mass. And we could find our value for anywhere in between those two, our mass anywhere between them. So let's have a quick look and think about how we can do that. So the first one we're going to look at is block A. So block A is pretty much got nothing much to do with this, but it is going to allow us to work out what is pulling the B value up the slope. Well, the A value has only got one force acting on it, and that's its weight pulling straight down. So its weight is pulling straight down. It's got a mass of 100 kilograms. So be careful, that's its mass pulling there. So it's got a mass of 100 kilograms pulling downwards. What's its tension? Well, its tension is going to be equal to the force pulling down. So if you've got 100 kilograms as its mass pulling down, tension is going to be 100 G, which is 980 newtons. So we know it's got a frictional force trying to move that block downwards with a tension of 180 newtons. Now, why that's important is because we now know if that tension has a force of 980 newtons in it, them 980 newtons are exactly the same all the way at any point on that string, on that wire, whatever it is, it's a string. Anywhere that string, it has a force of 980 newtons, including just here, pulling block B up the slope. Okay, that's what we mean by connecting bodies. Now we've figured out that tension just there, it's got to be exactly the same for this bit just here. And I can now ignore A completely. A is done, it's helped us out, it's given us a force that's pulling block B up the slope. Right, so now we can move on to B. All right, and we can think of the other forces acting on B. So B has a weight pulling straight down, which we know is going to be mg. It's pulling an angle 15 degrees. Just be careful, make sure you consider this bit. If you've got this as 75, that's just as good. Okay, you can clearly see the angles working in there. All right, the alternate angles, so we can see that will be 75. So you can either have 75 or you can have the 15. It's your choice. You're getting the same answers. We can work out how much of that weight is pulling downwards towards the slope and how much is pulling down the slope, parallel and perpendicular. So we can sort that out in a minute. We've got the normal contact force that's pushing from the slope, pushing back on B. So we've got all this information, but we're looking at the block about to move. All right, so we're going to put the frictional force on in a minute. Now we know that the R value is equal to mg connected 15. So it's mg cos 15, or you could have had mg sine 75. It would have got you the same. So we've got our R value. So R equals 9.466 m. So that's us calculating what the normal contact force is. And all of these things are exactly the same. We're not even considering friction yet. We're not considering what's happening to B. We're just getting the information down that we definitely know. Okay. What we're going to consider then is the block is about to slide up towards the pulley. Now, if that block is about to slide up towards a pulley, in other words, it's a lot, the A is too heavy, it's starting to pull it down, then what's going to happen, because it wants to travel in that direction upwards, the frictional force is going to act down the slope. So it's going to pull it back down the slope. So it wants to slide up, but friction's pulling it down. So why does that matter then? Well, now we can set up and work out what friction is. So the friction is going to equal a little bit of this as well. All right, because that tension force, if it's about to move up the slope, that tension has got to overcome friction and a bit of the weight of B. All right, in other words, the mg sine 15. So the tension has got to work equal both of them. So, all right, so we've got that force pulling up. Can we sort this out? Yes, we can. We can substitute F in for mu R. We know the mu value is 0.15. We know the R value is 9.466 m. So we can substitute those two bits in. There we go, 0.15 times by the R value plus this bit of the extra weight that's pulling down here. And we know that it's going to equal tension pulling up. So everything pulling in this direction must equal everything pulling in that direction. So that gives me a mass of 248 kilograms. If I had that B value as a mass of 248 kilograms, it will be just about to move. All right, just about to move. Anything less than that, 247 kilograms, is too light, and that definitely would move. All right, so just thinking 248 is the least amount it could be, the very least amount it to be, that A is not strong enough to move it down. All right, if that's lighter, then A will pull it down. Okay, so we've sorted out what its minimum weight could be, its minimum mass. What about its maximum mass to stop it moving down there? Because obviously if that's clearly, let's say 10 million kilograms, it's just going to go straight down the slope. Okay, so what's its maximum mass to stop it from moving down? Well, most of it is still the same. The R value is still the same. This bit's still the same. The tensions are still the same. The only thing that's different is if it's about to slide down the slope, friction acts in the opposite direction. So the frictional force will actually act up the slope because it wants to go in this direction. So friction will act in the opposite direction. Okay, so that's important. It wants to go down there, so friction is going this direction. So you've always got to consider where your limit in equilibrium is, which direction it's going to move. So in this case, what now? Well, now I can still set up the force diagram exactly the same as before. So what's acting on this B? It's in limit in equilibrium, so it's about to move. So if I look at resolving down the slope, because I've already got my R value, I've already resolved perpendicular to the slope, so it's parallel to the slope. I've got this weight here, okay, so that's mg sine 15 or mg cos 75 if you did it with 75. So mg sine 15, and the reason why it's not moving is because the frictional force and the tension from this weight pulling here, these two forces are equaling it out, okay? They're equaling it out just. Any more weight and it's going to overcome them, but at the moment it's equaling them. Right, so I can put the stuff in that I know. So I've got mg sine 15 is that. F is mu r, so I can put in the 0.15 times 9.466 m. So I've put my F equals mu r in. The tension, 980. A little bit of rearranging gets me a mass of 878 kilograms. So therefore, it will remain in equilibrium as long as the mass is less than 878 kilograms. Anything more than that, 1,000 kilograms, that's heavy enough because this bit of its weight here to overcome A being pulled in there, and it will the whole system will slide around like that. Okay, that means I have got now the two masses and that M has to be between to keep it in equilibrium. These are the two limiting equilibriums, but anything in between those, let's say 400 kilograms, won't move because the friction is too high. Okay, so just pause there, make sure you've got down what you need, and well done for following that. It's quite a tough question. Okay, speaking of tough questions, that's the sort of thing you guys need to be practicing now. So there's lots of different questions they could ask you. They could miss out certain parts. So in that previous question, I missed out the mass. You've seen questions where I missed out the coefficient of friction. They can miss out certain parts that you need to calculate. But the main two formulas that you're definitely using are the F equals ma, that you've known used for quite a long time now, but we're also using friction equals mu r, or friction is less than or equal to mu r if it's still in equilibrium. Okay, so make sure you spend plenty of time on those questions, please, guys.